In this clip, we'll go over in a bit more detail the solution to video exercise 2. The first question relates to prediction, which is a slightly more general example than given in the lecture, which considered the AR1 model. We consider now prediction from an AR2 model. So again, remember, when we're looking at the properties of predictors, we don't just assume the errors are correlated, we work with the IID assumption that the errors are IID, which just means that the average value of epsilon t plus d given any outcome of realization in the past just equals the unconditional expectation. This just says the average value of the shock in any time period is unrelated to the outcome in the previous period. Okay? And again, we always maintain that the average value of the shock is not. So throughout, we use shorthand that the expectation of any variable given the sample outcome, we just write it as E of the variable given yt equals little yt. So remember, capital Y refers to the random variable and little y refers to the sample output. So this just says the average value of whatever variable it is, given that we observe this particular sample outcome, which is our data. So first then, the predictor for t plus 1. So the idea is we have data up to time t, and we then want to use that data to predict what we likely believe the next outcome will be one period ahead, i.e. y hat t plus 1, our predictor, is just the conditional mean of y next period given the sample outcome we observe. So this is by definition. Again, what we can show is that under the IID assumption, this will be the best predictor. It will be as near as possible to the actual outcome next period, which again, I'm not expected to prove here. So we just plug in then, we plug in yt plus 1. So again, we just use the formula for, yt, forward one period. Okay, plug it in here, and then to expand out. So again, the average value of alpha given y alpha just a constant, plus phi1 of the expectation of the random variable yt, given yt equals the sample outcome, and again, plus theta 2 expectation of the value yt minus 1, given the sample outcome we observe, plus expectation of the error next period, given the sample we observe. Okay, so again, the expectation of the sum is the sum of the expectations. That also holds for conditional expectations. So again, the average value of yt next period, given that yt equals little yt, is just little yt, sorry about that. And again, the average, so again, when we condition on yt, then we know exactly what the value it took. Therefore, it's no longer random, it's just fixed. And the same for yt minus 1, we know what value it took. These just the sample observations. Okay, we're taking expectation under the assumption that we know what the outcomes were in the past, which is true because we have data up to time t. Finally then, we use the IID assumption to say that this equals naught. So again, we use the assumption above, then we can show that this holds by IID, where we assume that the average value of the shock is naught. Okay, so throughout any of these derivations of prediction, we're always assuming the expectation of the shock in the future given the sample outcome just equals naught. And this holds because we assume these errors are IID, which is somewhat stronger, they are independent, which is stronger than the assumption that they're uncorrelated. Do the same for yt plus 2. The best predictor is the conditional mean 2 periods ahead given the sample we observe. So again, plug in yt plus 2, go forward again, and expand it all out. Exactly the same as before. So now we get, well, what's this here? This by definition is just the sample this is just the predictor from t plus 1. Again, the average value of yt given we know what it is, it's just a value itself, it's fixed. And again, this term equals naught by IID and the mean naught assumption. So we get to this line here, and then we can just plug in the predictor from here into there and expand it out. So this here is the best predictor at time t plus 2 as a function now of the sample observations which we have. So again, the predictor can only be a function of the parameters, which we're assuming here that we know what they are, and all data we observe. Okay. So that's the derivation of the best predictor in an AR2 model, 1 step and 2 step ahead. Again, the same idea extends to the case of an AR3, AR4, it's exactly the same idea. Okay, so we can also then derive the forecast error. So, well, what we can show is by IID, and again you can just remember this result, the variance of YT I periods ahead given the sample outcome just equals the variance at YT plus 1. Because again, the effect, because YT is IID, the effect of the past doesn't influence now. So the variance of the process I periods into the future doesn't depend upon the sample outcomes in the past under the IID assumption. So it's very simple then, we just work out, we have YT plus I, we know what the predictor is, we can then just work out then the sample variance. So again, this is YT plus 1, minus this here is the predictor, and again, therefore take one from the other, we're left with epsilon t plus 1, and this here, by the white noise, IID, is just sigma squared. Okay, and the same for the forecast error at time period 2. It's the variance of the sample predictor. Again, plug in YT plus 2, and this here is the best predictor. Now, we're going to be left with epsilon t plus 2, plus phi1 of YT plus 1, minus the predictor. And again, from before, this difference is just epsilon t plus 1. So this here is epsilon t plus 1. Then we're done then, and notice this here is just an MA1. And under the IID assumption, they're uncorrelated, they've got the same variance, we can expand it out, use these assumptions, and we can show the variance equals 1. So again, you can refer back to your notes on the standard MA1 proof. Okay, so we derived the 1 step ahead predictor and the 2 step ahead predictor, and also looked at their forecast error into the future. We can see then, if phi1 doesn't equal naught, then the forecast error at time period 2 is greater than the forecast error at time period 1. Okay, and as the forecast error goes into the future, the forecast becomes less and less accurate. And it makes sense that the forecast into the future is going to be less accurate because, of course, the outcomes today in a stationary process the effect into the future is dying away very rapidly. So we should expect that the forecast error would increase as we increase the forecast period. Okay, so this just repeats a lot of what was said in the lecture, but for the example of an AR2. Okay, so we'll now move on to seasonality. So this question then refers to demeaning a variable and looking at deriving the mean in a seasonal series where the mean can change every quarter. So this D1 is a dummy which equals 1 in quarter if time period t is a quarter 1 observation and not otherwise. D2t equals 1 if time t is a quarter 2 observation and not otherwise, and so on. Okay? So we can see then the mean may vary if alpha 1, alpha 2 and alpha 3 don't equal naught in different quarters. So the aim is to derive the mean in quarter 1, the mean in quarter 2, the mean in quarter 3 and 4. We saw for example in sales data, say wine or retail sales, we saw the mean in quarter 4 tend to be much, much higher, which around Christmas, than the mean in quarter 1. So it's highly likely in some particular types of seasonal data that the means will not be equal in different time periods. And this is the simplest way of allowing the means to differ in every quarter. Okay, so the idea is that any time period t, if we have quarterly data, we've got quarterly data here, each one has to be a particular quarter. Okay, so every year we have 4 quarters. Okay, so if we first start with quarter 1, when q equals 1. Well, what's the average value of yt given we're a quarter 1? Well, by definition of the dummy variable, the dummy at 1, because t is a quarter 1 observation, the dummy equals 1, and all the other dummies equal 0. Therefore, using the equation here, plugging in this, we find at q equals 1 that yt looks like this here. It's alpha 0 plus the constant alpha 1 plus then we have this AR2 term and this MA1 term here. Okay, and again we're assuming stationarity, so we can take means on both sides. These are both constant. We have the average value of yt minus 2 given that time t is a quarter 1, and again the average value of epsilon t and epsilon t minus 1. So both of these are not by white noise. Okay, so then if time t is q minus 1, then what period must t minus 2 be? Well, 1 period back would have been quarter 4, and 2 periods back would have been quarter 3. Okay, sorry, there should be a 2 here. So the average value of yt minus 2, given that t is a quarter 1, is just the average in period 3. So we can just plug mu3 into here, and we have then an equation which the mean in quarter 1 and the mean in quarter 3 must satisfy. And we can do the exact same thing at quarter 2, quarter 3, quarter 4. So at quarter 2, the dummy at 2 equals 1, and the other dummies equal 0. So this time, when we evaluate, we get that this equals 1. So we pick out the alpha 2, and the other 2 equal 0. So we get that if yt is quarter 2, it looks like this. And again, take averages on both sides, conditioned upon the fact that q is quarter 2. So sorry, I've made a type. This should be alpha 2 here. Okay, and then we have the average value of yt minus 2, given that time period t is a quarter 2, and again these two terms both equal 0 by white noise. Well, if time t is quarter 2, then last period was quarter 1, and 2 periods back was quarter 4. Therefore, we have that this holds here. So we have a relationship which the mu2 and mu4 must satisfy. And we can keep going then. So we can do the exact same thing for 3 and 4 as we did before. We now have 4 equations in 4 unknowns to solve for the sample means. Okay, so we can just substitute and rearrange. So we can start by plugging mu1 into mu3. So we can plug mu3 into here, into the equation for mu1, and we get to here. Then we can expand out and solve, and we get down to this here. So we're solving a simple algebraic equation. We can then put back in mu1 as solved into mu3 to solve for mu3. We could do the exact same thing then for mu2 and mu4. So that's left as an exercise. Okay? Finally then, ask you to derive the variance. It looked harder than it was. Well, what's the demean? If we demean the series, then use the equation from before, we're just left with this MA1 term here. Therefore, the variance of the demean series is just the variance of this MA1, and again, because they're both uncorrelated, the variance of the sum with the sum of the variances, both the variances are equal sigma squared, and we get the variance of an MA1, okay, which we've derived before. Okay, so that's the end of this.